Hello, everyone, and thank you for joining us today. My name is Michaela McShane, and it is my privilege to welcome you to the Startup NASA Feature Series today, featuring robotic systems. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have questions, please type them into the chat box in the lower right-hand corner of your screen, and we'll answer them during the Q&A session at the end. This monthly series provides an opportunity for NASA technology-inspired startup companies to share their stories, including how they got involved with NASA and where they are currently in the development of their products or service. NASA's Technology Transfer Program ensures that innovations developed for exploration and discovery are broadly available to the public, and our Tech Transfer Expansion Program augments that mission to include a focus on entrepreneurial innovation and strategic partnerships to accelerate commercialization. We invite you to visit the NASA Tech Transfer website for more information on available licensing opportunities and other initiatives. And be sure to stay tuned at the end of the presentation for registration information on upcoming Startup NASA Feature Series events. Thanks for joining us today. It's my pleasure to introduce our speakers, Eric T. Long and Larry Feinberg. Eric T. Long founded Orbotic Systems to address the growing threat of space debris. Alarmed by the issue, he decided to take action and create Orbotic Systems as a solution for protecting spacecraft. The company has already developed its first product and is set to be available in early 2023, with plans to build a satellite constellation to record space weather conditions for debris remediation and make the data available for research organizations. Eric has over 20 years of experience in the technology industry, including project management and a master's in science and space studies and aerospace science from American Military University, a graduate certificate in information technology project management from American Military University, and a postgraduate diploma in economics from the University of London. He is also a member of Project Management Institute. Eric is joined by Larry Feinberg. Mr. Feinberg worked in the aerospace industry for over 35 years, primarily at NASA's Kennedy Space Center. During his 20-year tenure at Boeing, he served as KSC's Design Center representative for the Space Shuttle Orbiter Main Propulsion System. In 2004, Mr. Feinberg transitioned to NASA Civil Service in the Launch Services Program and served in an oversight role for Atlas V and Delta II Launch Complex mechanical systems. Prior to Mr. Feinberg's retirement from NASA in 2018, he became interested in issues related to space junk and arranged for his team to create a prototype of a device which could be attached to a small spacecraft, such as a CubeSat, for end-of-mission controlled demise scenarios, including a targeted Earth atmospheric entry point. This project evolved into the D-Orbit drag device, D3. Mr. Feinberg is also a part-time adjunct professor teaching aerospace design capstone classes at Embry-Riddle Aeronautical University in Daytona Beach, Florida. With that, I'd like to welcome Orbotic Systems to share their story.
Thank you, Michaela. I appreciate the introduction. That was great. And I also want to thank everyone that's here today and wants to learn a little bit about Orbotic Systems and our primary technology, which is the D-Orbit drag device, or D3 as we like to call it. So just to give you an overview of what we'll discuss today, I'm going to go ahead and show you here, if I can, what we'll be covering. So Orbotic Systems really came to fruition after working with NASA and engaging in a licensing agreement with them. And so the first part of this presentation, I'd like to give you an introduction to the company at a high level, and then also introduce you to the problems that we're facing, primarily the space debris issues. Then also we'll move into working with NASA, how Orbotic Systems got involved with NASA and the very positive outcomes that came from that. And then the fourth subject that we'll cover toward the end of the presentation is what we're doing now, our future plans over the next year or two, and some of the products that we're working on. So as Michaela mentioned, my name is Eric Long, and I'm the founder and CEO of Orbotic Systems. I created Orbotic Systems with the intention of finding a problem, or a solution rather, for the problem of space debris. And this became a difficult situation because I wanted to approach it from a technology and business perspective. And most of the people that I spoke with just a few years ago thought that that was really going to be difficult, if not impossible, to do at this time, because no one could really understand how you could make a profitable business out of the space debris issue. And as it turns out, there are many other companies that were facing the same types of problems and also questions. And as it turns out, we came up with a solution, and this was really due in large part to the technology that came out of NASA and also that was developed in part by Larry Feinberg, which we'll get into in a few minutes. So just to give you an overview of the company again, the mission, the vision and the mission of the company. The vision is to address the growing threat of space debris. And we want to do that with both the business and technical perspective. And then the primary mission, at least at this point in time, is to release our D3 and mitigate the space debris that's going to be created in the future. So we like to say that the D3 does 80% of what rockets do at 10% of the cost, and it does this without using any type of propellant like a standard rocket thruster does. Most of you probably are aware of space debris and that it's a huge problem, but just to give you a little bit of a background in case you don't know some of the numbers, space debris in itself has really become an existential problem because not only is it a threat to human life in space, such as debris that may strike the ISS or astronauts, it's also a threat to access to space. And as it turns out, a huge amount of the technology that we have on planet Earth right now depends on satellites that are in space, and a large number of those are in low Earth orbit or LEO. So LEO seemed to us to be the obvious first choice to search for a solution to the space debris problem. If you look at some of the numbers, and this is based on data that came out in 2021, you're looking at what you can see here, 27,000 pieces of space junk that's tracked by the Department of Defense and the Space Surveillance Network, 23,000 larger than softballs, and they're traveling at 28,000 kilometers per hour. You have about 500,000 the size of a marble or larger, and then you also have about 100 million greater than 1 millimeter. And so again, most of these are in low Earth orbit, and actually the number has increased quite a bit just in the last 2 years. Now, the government has started to make a turn in the right direction in terms of their engagement with the space debris problem. And this really started last year, at least the US government. So what happened that was really revolutionary in the area was that in September, the FCC decided that they were going to expand on NASA's 25-year mandate and make it a rule that, make it a rule that a small spacecraft that's going up into orbit has to reveal or produce some sort of solution in advance that will remove that spacecraft from low Earth orbit or at the time of the mission life cycle completion. And this is actually a great entry for companies like Orbotic Systems and others that are in the space debris field, because now it is no longer just a suggestion or a mandate, but it's actually turning into a law. Our solution is a pre-launch remediation solution. So while it would be great to go ahead and be able to send up satellites that can grab onto a piece of debris and bring it down, that's a rather difficult task to do, and there are companies working on it and making great strides. However, our focus is to take technology that we develop, make it available to the small sat operators so that they can attach that to their satellite prior to the launch. And then once their mission is complete, the technology, which in this case is our D3, will be able to deorbit the satellite without using any propellant. So that removes the explosive element and the other threat of danger that comes from that. Traditional propellant thrusters, while they certainly have their applications, are not necessarily the best course of action for a remediation strategy. You have a number of different issues associated with that, including weight from the extra fuel. There's an explosion risk that's associated with the fuel. There's also more cost involved, one in just building the thruster and controlling it, and also the extra weight that is necessary to be lifted into orbit. And then you have to worry about fuel depletion, and just the general risk mission failure is higher. With The D3, this is the Orbotic Systems answer, you eliminate many of the issues that are involved with the standard thruster. So what the D3 does is it inexpensively and effectively deorbits the small spacecraft. And it does this by using booms that can be retracted and extended. Those booms are controlled by a computer algorithm that was also developed by us and NASA. And this is used to modulate drag and take control of the spacecraft up to about 700 kilometers. We'll get into a little bit more of the details as we proceed, and Larry will explain some more of that to you. So again, why use the D3? Well, the D3 costs a lot less than rocket thrusters. There's a backup system, even if you do have a rocket thruster on your spacecraft, so that you can still control it in case that thruster system is no longer functional, or it runs out of fuel, or something happens to it. You also have the attitude control capability, so you can change the orientation of the spacecraft. It's not just for deorbiting. You don't have the hazardous materials, you don't have the explosion risk, and then also you can use various types of hardware. So you don't need to necessarily use some high strength hardware like titanium to build it. Risk and liability, I just wanted to touch on this briefly. When I mention risk and liability, I'm not just talking about the risk of taking down the spacecraft after the mission is complete, but also the liability of running into another spacecraft, or the insurance costs that are involved. So with a D3 on board, you're going to be able to reduce both of those. At a real high level, I want to go over the concept of operations, or the CONAPs of how the D3 will operate. What happens is that in most cases, you're going to have the small sat that's launched on, say, call it a SpaceX CRS mission, and then the spacecraft will be deployed, typically from a deployer mechanism like a NanoRacks. And then once the satellite is deployed from call it the NanoRacks deployer, then the D3 is activated and it stabilizes the satellite. Then communication is made with the D3 and presumably the satellite, depending on the mission profile that the operator has. Once the mission is complete, then the D3 will activate and find a targeted location to deorbit the satellite. Now I'd like to introduce again my colleague and VP of Product Development, Larry Feinberg. He has extensive experience with NASA and Boeing, and he's going to jump in here. I'm going to hand off to him, and he's going to tell you a little bit about the history of the D3 and his work on it with NASA.
Hello. So I'd like to start off by mentioning that when I joined NASA back in the 2004 timeframe, spent a little bit of time on the Launch Complex Mechanical Systems, but after that, I transitioned into becoming a senior integration engineer on a variety of spacecraft, and they're listed on that chart. But basically, both big and small spacecraft. And as part of that, and around the 2010 timeframe, we started to become, from a NASA perspective, we started to become interested in launching and deploying small spacecraft such as CubeSats. So basically, utilizing the excess performance from some of our rockets and some of the primary, after the primary payload is released, there was still excess performance. So why not utilize that? So we began work on the CubeSat launch initiative, but at the time it was really referred to as Alana. And we came up with a set of program requirements for CubeSats to meet in order to launch on NASA missions. And so born out of that was a lot of the launch initiative stuff that we see today. And so in about the 2014, 2015 timeframe, we used some research dollars. I was still at NASA. We used some research dollars to look at ways to control CubeSat orbital debris. So basically, when the CubeSat mission was done, when their mission science was complete, it was a way to bring them down to Earth orbit, and so from Earth orbit down to a lower altitude. So on this chart, you can see a comparison with D3 and without D3. And based on our analysis, we show a marked reduction in orbital lifetime with D3 deployed. And so, for example, for spacecraft at 700 kilometers or less, which is the orbit regime that we're targeting, the orbital lifetime with D3 deployed is significantly lower than without D3. And I'll be referencing quite a bit ballistic entry point. And so your orbit can be reduced up to a point where there's enough atmospheric drag for ballistic trajectory to take over. And so D3 is really in the regime of about 120 kilometers up to about 700 kilometers. So from the physics of what's going on, if you could back up one chart, we depend on the ballistic coefficient primarily. And so that's the ballistic coefficient of the spacecraft. And we're going to modulate that using the D3 deployed booms. And so we can bring those in and out to alter that coefficient. But we're relying on a certain amount of atmospheric density and solar activity, and also gravitational effects of the Earth and Moon. So what happens is D3 can roll the booms in and out similar to a tape measure. That changes the ballistic coefficient. And the reason why that's important is, and the reason why it could be variable is, so the atmosphere responds and changes with solar activity. The more solar the activity there are, the atmosphere generally expands, and that changes the drag profile of a lot of spacecraft. So it can change on a daily, monthly, yearly basis. So with D3, what we've outlined is the booms and the motors themselves occupy about a half a U. So from a CubeSat platform, that's a half of a 1U CubeSat. That leaves, so in the example of a 3U CubeSat, which is a common device that's flown, that leaves about 2 to 2.5 U available for the primary payload or for the mission science of that mission. So our D3 would interface with the payload for a mechanical interface, and there would be a power interface. And our device is scalable from a 1U size to about 400 kilograms. So here you see on the right-hand side, deployed configuration with D3, without D3, I already showed that picture. So the advantages are you can identify your spacecraft early. So especially if you're in a constellation of other spacecraft, it can be difficult until you pick up the beaconing from a particular spacecraft to identify which one is you. So when you deploy the booms, it increases that radar profile and increases that visibility. In addition, we're able to comply. The original, at the time when we developed it, it was the NASA 25-year policy. We've since come down, and we'll be able to meet the FCC 5-year rule. So we use altitude decay control, and we can plan that orbital decay. We can speed it up or slow it down depending on the amount of drag we employ with the booms. That gives us a controlled reentry and a targeted impact point. So that's that ballistic trajectory again. So we can target an area that may be unpopulated over the ocean, that type of thing. And we talked about the scalability. So from a 1U CubeSat up to about 180 kilogram small spacecraft. We've done quite a bit of Monte Carlo analysis of the targeting accuracy. So you can see a graph there. And then the applicable case classes is shown on the right.
Okay, thank you, Larry, for that detailed explanation of how the D3 works. Based on that last slide and the information that was presented on it with the weight, I thought this would be a good time to present some information on the small satellite market itself. We didn't really touch on the business of debris remediation and the D3. So if you look at this slide here in the spreadsheet, you can see that there's a list of different types of classifications for satellites, small sats, and different weight categories. The D3 is capable of handling, under its current design, a weight of up to about 180 kilograms, as Larry mentioned, and 12U mass. So we did work on scaling that up with one of the team leaders and inventors Dr. Bevilacqua, and we had a discussion with him about the maximum weight that we might be able to utilize with it. So as it turned out, we looked into larger satellites, including the size of the Starlink satellites. And according to the modeling, there's no reason why we can't scale that up. So we expect to be able to expand into the larger medium satellite market as we develop further into this. And you can see from the growth rate of the satellite market that it's growing extremely fast, and the projections to 2030 are just incredibly high. And I mean, we're looking at possibly 60,000 small satellites in orbit by 2030, and they all need a remediation and a deorbiting solution. So we feel that we're in a good position to assist the space operators in deorbiting their satellites. There's other various mission concepts that we investigated, and one of those was attaching the D3 to an existing satellite, such as the ELSA D from Astroscale, that's designed to attach to debris and then take it down. And we actually had a discussion with them about it. One of the concepts was to go ahead and lower the altitude of their satellite without using fuel, and then when they needed to go back to the position or the orbit where they could attach to existing debris, then they would use their fuel source. So it would be a huge fuel savings. One of the other applications is taking the debris and utilizing what I mentioned some time ago in the presentation, where you would take a small satellite with some sort of a gripper mechanism on it and then attach to a piece of debris, and then the deorbit would take place once the D3 was put into action. And then a third concept that's also feasible is extending the life of an existing satellite by taking, for example, another small satellite with a D3 on it, attaching to an existing satellite that may not be working because of an orientation problem, and then using the D3 to change that orientation so that it can activate again. One example might be the orientation in regard to the solar panels. Something may have happened where it's not able to collect enough energy to power up. So just a few ideas for you to think about in terms of other applications. So what's next for Orbotic systems? We're focusing on what we call the DART cube, and the DART cube is kind of a derivative of the D3. It stands for it's an acronym actually, and it's debris avoidance and removal technology, and the cube is the actual cube shape of the device. So we envision it will look something like this diagram, where you'll have a 1U device that bolts onto an existing satellite, but it's completely autonomous in the sense that it has its own solar panels and power source. It has a D3 on it with a GPS beaconing system, and it also has a satellite communication transceiver so that it can talk to an existing satellite network. So if you can imagine that with the DART cube, you don't necessarily have to have a lot of the other technology in your satellite system. It's already built in, and then it's bolted on, and then you can control the software or the D3 independent of your own satellite solution. We feel that there's a lot of applications for this. Just to comment on the DART a little bit further, there's also two different concepts for the DART. One is just a D3 only DART, and then the concept two would be a propellant DART. So I already explained the concept one, more or less, the D3 DART, but if you can envision using the DART in conjunction with the satellite that also has a thruster system, there would be the added benefit of lowering the orbit or changing orientation without using the fuel in the thruster. We're planning on doing a test launch for a DART, and this is the schedule and the milestones that are already in place. If everything goes well, we expect to do the DART launch in March of 2024, and we'll certainly be happy to keep you updated on the results from that. So in summary today, the D3 modulates spacecraft drag force and controls the orientation during orbital decay. All of our testing has shown positive results. We did do a launch in last summer in August, and then we deployed the launch was actually in July 14th on a SpaceX CRS-25 mission, and then we deployed it in September from the ISS with nanoracks. And another advantage to the DART is that it comes with a deorbiting and targeting algorithm that's designed to work exclusively with it. And also the analysis that we've done has confirmed that we can scale up the D3 for larger spacecraft. Another benefit is that you can improve the radar visibility of the spacecraft by extending the booms, and will allow you to identify your spacecraft if it's in a constellation or if you're integrating with a constellation. Another advantage is that it helps in space traffic management, orbital debris mitigation, obviously, and controlling the satellite. And then also you can do a CAM, a collision avoidance maneuver. So that opens the door for a lot of other possibilities as well. And then just the orbital deployment in general, because you can change the altitude without deorbiting the satellite. We expect that the use of the D3 is going to expand the operation regime for satellite operators and also allow them to use different materials, because if you can have a precisely targeted reentry, then you may be able to use materials that would normally not be allowed to be used because of the fact that they would survive reentry. So I just wanted to give a shout out to some of our partners and associates that we've been working with. This is by far not all of them, but we are in contact with them regularly, and they've been very, very helpful. And I also want to say thank you for your continued support in the debris remediation problem. And last, the D3 is available now. So if you want a D3 for your spacecraft mission, you can contact us. The website's listed below. You can reach us through that, or give us a direct phone call, or you can email us at our administrative email, and we'll be happy to get back to you with more information. Just as a side note, currently the workflow is 90 days. The D3 is made to order. So from the time that you place the order to the time that it's delivered, including testing, you're looking at about 3 months. And with that, I will return the presentation back to Michaela.
Thanks, Eric. And thank you, Larry. That was an excellent presentation. If it's okay with you both, I'll go ahead and get into the Q&A.
Sure.
Okay, perfect. So to start out, what would you say is the most important lesson you've learned along the way that's helped you grow your company?
I would say that it's all right to ask for help, and there's a lot of resources available, and NASA's willing to provide them to you. And working with NASA has been really an incredible experience. And just to answer that with a short story, I don't want to to make this too long, but I was really nervous about approaching NASA the first time I did and asking them about help with technology. And in hindsight, that really was unnecessary, because they've been nothing but willing to work with us and help us improve our technology and get it out to the commercial market.
Perfect. And as a follow-on to that, how did you first get involved with this technology and find out about NASA technology transfer as a program?
Sure. So the idea for the company really started around 2017, and I went to a SpaceCom, and it was essentially, if you don't know what SpaceCom is, it's a trade show for spacecraft operators, and NASA was there, and they had a booth, and they were talking about working with them in the technology transfer program. So eventually in 2019, and even more so in 2020, when I actually engaged with NASA and met Larry, that's when we started. So there's plenty of information also online if you do a search for technology transfer, and again, they're more than willing to help you out.
Thanks. Shifting to more of a hardware-specific question, are the individual booms similar to a tape measure mechanism, a coiled curved length of metal that can be deployed to lengths as necessary to adjust the drag? What boom lengths are available?
Sure. Larry, you want to answer that?
Sure. So That actually was how part of the idea was generated. Was, hey, wait, why can't we deploy these like a tape measure? So that's exactly right. And so the boom length is on the order of about 3 meters, and the boom width is about 3 to 4 centimeters in width. And we played around with those dimensions quite a bit to determine what is the optimal drag area. And so University of Florida, Dr. Bevilacqua, Dr. Sandy Omar, and Dr. Dave DiGuglielmo were really critical in helping us figure out what was that optimal drag profile area and the controllability aspect of it for sure.
Okay, great, thanks. And then similar question, what is the mass of the system?
You want me to take that?
No, go ahead. I mean, the mass of, do you mean
Go ahead.
the D3 in general?
I'm assuming that's what it means, yes.
Yeah, so you're looking at about roughly 1.6 kilograms, if I remember correctly.
Okay. And is it a standard size unit for every
I'm sorry.
spacecraft?
Yes. Yeah, the mass. So it's 1U as it stands now. We're looking at shrinking it down to half the U, and that's part of the reason is so we can integrate it into the DART concept. But as it stands right now, yeah, it's almost perfectly 1U.
Okay, great, thanks. So the unit itself, it fits. I guess does it work on any spacecraft? Does it have to be adjusted for larger, smaller ones?
Go ahead, Larry.
It's designed to fit into the standard CubeSat deployers that exist today. So a NanoRacks deployer or a Cal Poly Peapod deployer, and so it would fit within those dimensions. But certainly on the specific spacecraft application, the motor assembly, the boom assembly, and there's a couple adapter boards that go with that. Those could be modified for pretty much any small spacecraft profile. And we're working on a standard set of mechanical and electrical interfaces. We pretty much got that down, but there would have to be some tweaks to customize it to a different type of spacecraft.
Okay, thank you. What were some of the biggest challenges that you faced in the early stages of the company, and how did you overcome them?
Well, I would say that going back to what I had touched on earlier regarding combining the technology and the business elements into a concept that could be followed were difficult because one thing is to find a technology solution. The other thing is to find a business solution and then marry the two together and make it work. So in part, the timing was good because of the fact that more and more people, including the governments of the US and Europe through European Space Agency, have recognized that space debris is a huge problem. It's a societal problem. It needs to be addressed. So that helped. But I would think that you should plan out both sides of it if you're starting on that endeavor. Think about it from a high level first and then sort of drill down into it.
Great, thank you. Are you considering supplementing control with reaction wheels?
Sure. It all depends on spacecraft size, moments of inertia, location of the CG. So it absolutely can be done. But the idea is a passive system. Reaction wheels, of course, require power. There's a certain degree of complexity to it, but if you're interested in additional stability and control, absolutely.
Yeah, just to add on to that, the original D3 was using magnetorquers, and that's something that we still are considering for certain applications. We wanted to get away from any type of a supplemental orientation device like a reaction wheel or magnetorquer, but of course, depending on what you're using the satellite for, it's easy to go ahead and modify that. So maybe the first step would be magnetorquer, and then if you really needed a little bit more torque, you could use a reaction wheel.
You mentioned in your presentation that this reduces cost overall. What is the actual cost of the system, if that's something you're at liberty to disclose?
Yeah, sure. And there's also that reminds me of a point that I didn't mention, I don't think, was that most satellites require an ADCS, the Attitude Determination Control System. So a great thing about the D3 is that in many cases, if not most, you can eliminate that ADCS and just use the D3. So it has that additional benefit and cost savings, which can easily be $50,000 or more. Right now, the D3 is priced at $40,000 or less, and that includes integration and consulting.
And, you know, I'd also like to add, kind of back to Eric's point, you know, it to a certain extent, it takes the load off of a spacecraft designer, CubeSat designer, because in their mission planning, all they really have to worry about is what it takes to perform their mission and not the demise of the spacecraft. And so the idea is the spacecraft operator, they perform their mission science. When that's over, let D3 take over from that point.
Perfect. Thank you both. I think that's all the time we have for questions today. So I want to thank you both for speaking on this platform. I think it was a very informative presentation, and I hope that everybody got a lot out of it.
I hope so too. And once again, thank you for joining us. And I appreciate it, Michaela.
All right.
Thank you.
Thanks, everyone. Have a great afternoon.